I actually had a class working in here this afternoon, and while the class was doing things, I was doing that maths on the board and went and fished out the parts to use in our little lab. So without any further ado, let's get on with the lab. Here I've made a quick sketch up on the board of the transistor circuit that we'll be using in this small lab. It uses a 2SC549 with a beta of 320, which was measured on the multimeter this afternoon. I've worked out that I need, with 9 volt supply, around 4.6 volts at the collector of the circuit, and if that holds true and I need 10 microamps at a guess of base current flowing into this transistor, I can do some quick maths on that, and I can take the base emitter junction away from the 4.6, run with 4 volts across with that 10 microamps of current, and then I'll work out that I should get around about 330k, I think it was, for that resistor. I chose to run with a 390k to start with, and then I found in some part of a lab that I needed to put a higher resistance because I had too much base current. Now, I ran the maths on that, and I worked out pretty quickly at that Q point at 4.6 volts, I need around about 3 milliamps of collector current. I said here I'm aiming for 4 volts, that was the deal. Then I've rejigged the maths quickly on the board here in the workshop to match what I did in that first theory video, and by the time I get to the end of it, I've come down with I think I worked out that I get an IC of 3.1 milliamps, which was very, very close to my design of 3 milliamps anyway for this circuit. So there's the working out again quickly, and then from here we'll go across to the breadboard and we'll have a look at the actual circuit, and we'll put it through its paces. We'll measure the collector voltage, we'll measure the base voltage, we'll go ahead with 2 different values of base resistance. We'll use 390 and we'll use 860k, which is those 2 resistances in series, and then we'll heat up the junction of the transistor, monitor the collector voltage, see how much it falls and how quickly it falls with each one of those base resistances in circuit. So here's the final circuit. It's a very straightforward circuit, 2SC549, 3.3k resistor in the collector circuit. Currently I'm running with 390k ohms in the base, and I might just get the multimeter here and we'll take some measurements, and then I'll pan the camera so that we can see what we're looking at. Now, the mathematics did show that with around about 330k, 390k in the base, we should have had around about 4.6 volts on the collector. But in fact, when we take a look at the collector voltage, we find out that we've got around about 3 volts DC. That's a little bit less than where we thought we should be, so obviously we've got too much base current, and that's pulled the collector down just a little bit too much. If I go and look at the base, I've got about 660 millivolts sitting on the base, so that would appear to be turned on quite hard, I would think, for a small signal transistor. I'll just rearrange things here a little bit. I'll move a wire which will put effectively 860k instead of 390k now into our base circuit. And with that 860k in the base circuit now, if I remeasure the collector, we're at 4.48, 4.5 volts, and that's half of the rail voltage, which is effectively 9 volts. So that's quite interesting. Obviously, the 10 microamps of base current that we started to think about with the equations was too much for this particular transistor. Anyway, look, I'll leave that 860K in there, and I'm going to now use a soldering iron, and I'm going to put the soldering iron on the emitter of the transistor, and we'll take a note what happens to the collector voltage. So I'll measure the collector voltage, and again, this is with 860,000 ohms sitting on the base, and then I'll get the soldering iron and I'll hold the soldering iron onto the emitter. With the soldering iron on the emitter, look at that voltage. It's coming down. It's coming down quite quickly. Then take that away, and up it will go again. Now, in the simple base bias circuit, we did a similar experiment, and we found that the collector voltage dropped very, very quickly, and it did drop down to a very low value because there was no feedback at all in that simple base bias circuit. But in this circuit, even with a fair bit of heat going up the lead of the emitter on the transistor, it fell back, but it didn't fall back anywhere near the same amount as what we saw on the simple base bias. I'll just try that again, and I'll put the tip of the iron on the collector. We'll monitor the collector voltage. There you can see it's falling quite steadily, and there'll be a lot of heat now going into the junction of that transistor, and it recovers fairly quickly, as we saw with the simple base bias circuit as well. It'll be interesting to do this same experiment with the voltage divider bias circuit. The voltage divider bias circuit should have the best stability out of all three, but certainly the stability in the collector feedback bias circuit is better than the simple base bias circuit. I'll just do one more thing here. I'll bypass the 860K and put us back to 390K of base resistance. And there at 390K, our Q point has shifted severely. It's gone a lot lower because we've got too much drive going into the base. Be interesting to see what happens as far as temperature goes with the extra drive on the base. So let's have a try with that. If I can get into this circuit without burning things. Hate the smell of burning plastic with the soldering iron. Okay, there we go, shooting down. It's going to go down quite rapidly down to 2.15, 2.1. I think I'd probably cook the transistor before it got down to 2 volts. Ooh, that transistor's quite hot, yes. That's interesting. It didn't seem to drop as far with the extra base current going into it. It seemed to be a little bit more stable. So the added stability came at the cost of shifting the Q point from around 4.5 volts down to 3 volts. So that's an interesting thing to take into account as well. I did notice in one of the textbooks that it said that the Q point would be shifted down the load line. So there again, there's our little 2SC 549 NPN small signal transistor. And you can see I attacked it before with the soldering iron into the plastic top. Not a real smart thing to do because it did create some nasty fumes, and also did leave a pretty good mark in the top of the transistor. And that's not the best place to put the soldering iron for this experiment because you've got the thermal inertia of the plastic case. Much better to put the iron directly onto one of the leads and get the heat directly up into the junction. Alright, so look, that wraps it up. It was just a quick lab to show the collector feedback bias circuit, to stack it up against the theory that we did in the first video. So, hope that helps. This has been Greg Moore from TAFE with yet another lab in the series on amplifiers and BJTs. And here's our lovely workbench. This is our lovely workshop.